Okay, we're going to try and run through just some quick terms about segments. Some of them you've already read about, so we'll just blast through them. We're looking to be able to find the distance between 2 points in a coordinate plane, and I want you to conceptualize this as more than just an equation. Okay, first off though, we had a few vocabulary terms in this unit. One of those we've talked about multiple times: postulates, rules that are accepted without proof, and theorems are rules that we have to prove. So you're going to see a couple of postulates. I'll just blast through those because, again, there's stuff that we've kind of just accepted our whole life. So looking at the first postulate, and they number them differently in different books depending on the resource they're drawn from. So this is the first postulate that we all kind of have to accept, and that's the ruler postulate. That allows us to find distance and length. So just running through it really quick, it says the points on a line can be matched 1 to 1 with real numbers. So we can line up a ruler and actually measure this out. The real number that corresponds to a point is the coordinate. The distance between those are written as AB. And notice AB does not have a symbol above it. So if it doesn't have a symbol, I'm assuming you're talking about length. We also read it as the length of AB, or the distance of AB. And we can find that distance on a coordinate plane by taking the further distance away minus the shorter one. Typically we start at 0, we line it up, and we don't have to subtract. But if you line it up anywhere, you should be able to subtract the second or larger x-coordinate minus the first one. Another key word that we forget about a lot because we're not exactly sure what it means is between. In mathematics, when we see that word between in theorems, make sure you understand that if it says point C is between 2 points, boy, that's bad writing. Then, so if it says it's between A and B, it's not just anywhere. If A is here and B is here, then C has to be somewhere on that line between them. It has to be collinear. Okay, so as we look at that, look at the next theorem. It says in theorem 2, if the segment addition postulate, if B is between A and C, it's on the same segment, then AB plus BC equals AC. The two little pieces add up to equal the whole piece altogether. Only if B is in between. Wouldn't work if B was up here because you're off the line and not collinear. So we use that, that's a stupid example, we use that when we look at adding segment lengths together. You'll see a few problems on that as well. The last thing is the distance formula. A lot of you learned this in Algebra 1. The distance formula has to do with segment lengths and finding those in a coordinate plane. And the distance formula, which I don't see here, is written as the length of AB is one enormous square root, the square root of x2 minus x1 squared, plus the square root of y2 minus y1 squared. Most of us don't like to memorize those things, so let's take a look where that comes from. The x2 minus x1, that's that definition of distance. It is the distance when you subtract the x-coordinates. That's the length, or the horizontal distance traveled. The y2 minus y1, that's the vertical distance traveled. Well, I want you to think about that as the Pythagorean theorem. If I want to find the length of this value here, we'll call it C, then I need to find the length of A and B, because then I can do the Pythagorean theorem. A squared plus B squared equals C squared. Much easier to remember than the distance formula. Those are the same thing. This is the horizontal distance, or A squared. This is the vertical distance, or B squared. So if you do A squared plus B squared and then do the square root, you get that specific value of C. So if you were asked to find the length of any two segments, you should be able to do that, and we'll run through that in class together, finding if any of these segment lengths are the same. Now for me, well, we can run through this in class, but Again, it's all about making that right triangle, looking at distances. And on a coordinate plane, you can count that. So I know this is a vertical change of 2 and a horizontal change of 3. And then I would just do a squared plus b squared equals c squared and solve for that missing value. Over here, I would make a right triangle that looks like this. And from the center point A to D, I would make one like this. Okay, and you can see right away if this is a change of 1 and 4, this is a change of 2 and 3. Right now I can see from B to C and from D to A, they have equal measures or equal lengths because their horizontal and vertical changes are the same. Lots of examples, and we can run through some more together in class if we need to. Another term that you'll see often is congruence. Congruence, when it comes to segments, it doesn't make as much sense as it does with other shapes, but congruence is when not only do they have the same length, but then we start looking at the same shape. Okay, so congruence has a sign that's not just an equal sign, but it has a squiggle above it. If segments are congruent, you can't have a ray be congruent to a segment. Okay, because they're not the same shape. So when I think of congruence, I think same size and same shape. A square can't be congruent to a triangle because they are different shapes, even though they might have the same size. They're equal in measure, but not congruent. Okay? We're going to talk a little bit more in class. See you tomorrow.